Okay, in this video we'll talk about symmetric matrices. Symmetric matrices. So the definition is a square matrix is symmetric if it's equal to its own transpose. So for instance, if this matrix is called A, it's symmetric if A transpose is equal to A. So for example, if I have this matrix is symmetric because if I take its transpose, I get itself, and this matrix is also symmetric but if I had a matrix like I can even just do this. This matrix is not symmetric, right? 1, 3, 4, 1 is not symmetric because if I take its transpose, I don't get the original matrix. Okay. And of course, the identity is a symmetric matrix, and the zero matrix is a symmetric matrix if I have a square matrix. Now, the first property of symmetric matrices comes from the fact that you can actually produce a symmetric matrix from any matrix. So if A is any m by n matrix, then A transpose A transpose times A is symmetric. I mean, let's just check that this actually makes sense. So if A is m by n, then A transpose is n by m, and A is m by n, so then if you do A transpose times A, you get an n by n matrix, right? So it's a square matrix, so there is hope that it's symmetric. And we can actually prove this. So let's prove this. Well, what we need to do is we need to take the transpose of this matrix. So if you take A transpose A and transpose it, what do you get? Well, you can use the properties of transposes. So the property that we're going to use is this property that if I have A, B, and then transpose it, it's equal to B transpose A transpose. Okay. And if you apply that fact here, with your A being A transpose and your, okay, I should have used different letters, but your A will match with A transpose and your B will match with this A, then, and you just use this theorem, then you're going to get A transpose and then A transpose transpose. And that is going to be, so to get from here, I use this fact. And A transpose transpose, if you transpose twice, you just get itself, so this is A transpose A. And that's the proof. We started with A transpose A, we transposed it, and we got A transpose A. That means that A transpose A is symmetric. Okay. So now let's look at one property of symmetric matrices. A theorem is, let's say that let A be a real n by n symmetric matrix. And of course, all symmetric matrices are going to be n by n, right? Because if they weren't, then the transpose can't possibly match itself. Okay. And, you know, in this class, we're assuming that all the matrices are real, right? Real entries. So maybe I'll put that in parentheses, but it is important. Okay. Then all of the eigenvalues of A are real. Okay. Now, when you have an arbitrary n by n matrix, right, that's not necessarily symmetric, then its eigenvalues might not be real. So for instance, if you had right, this matrix with 0, 1, 1, 0, then it has eigenvalues I and minus I, right? So they have, the matrix has real entries, but the eigenvalues are not real. But it turns out that when you have a symmetric matrix, sorry, the matrix I was talking about is 0, 1, negative 1, 0, right? This is not symmetric, and its eigenvalues are not real. It's always a good idea to just have these examples in mind, right? Okay. But the theorem says that if you had a symmetric matrix, then its eigenvalues are real. Let's see if we can prove this fact. So there's a trick for this, and it's, let's see, what is the trick? Okay, so first let's let lambda be an eigenvalue of A. So we want to prove that lambda is real, and that's equivalent to showing that its conjugate, its complex conjugate, is equal to itself. Right. Okay, so let's say that V be a complex eigenvector for A with eigenvalue lambda. Okay. So you have, so i.e. AV is equal to lambda V. And now take the complex conjugate of both sides. Okay, so taking complex conjugates of both sides, we get A bar V bar is equal to lambda bar V bar. Right? Now since A is real, this amounts to saying that AV bar equals lambda bar V bar. Okay? Right? Because A is equal to A bar because A is real. And now, okay. Now notice it says consider lambda bar V bar transpose V bar. Okay, sorry, lambda bar V bar transpose V. Now what will that give us? So this is equal to, okay, well that's just lambda bar v bar transpose, that times v bar, and this is going to equal lambda bar v bar in parentheses transpose v bar. Okay, that's correct because you can just pull the scalar out. All right. Now this equals, okay. Okay, so I have lambda bar v bar, and that's equal to AV bar, right? So this equals AV bar transpose V bar, and this is equal to V bar transpose A transpose V bar, right? Because I'm just using the property of transpose. I have A times V bar, and when I take the transpose, I just reverse the order. And now this is equal, since A, okay, now we use the fact that A is symmetric. This is equal to V bar transpose A V bar. So here we use the fact that A is symmetric, right? Okay, and then this is equal to, so A times V bar is a lambda V bar, so this is equal to V bar transpose lambda V bar, and then we can pull out the lambda, so it's lambda times V bar transpose V bar. Oh, well, when you look at that, we got that this expression, this quantity, is equal to this. Okay, so let's write that out. So lambda bar V bar transpose V oh, I don't have bars here. Oops, sorry about that. There's no bars here. Okay, this is a bit of a mess. V. Okay, sorry, let's remove these bars. Okay, so yeah, lambda bar V bar transpose V equals lambda V bar transpose V. All right. So this is equal to, so this implies that lambda bar minus lambda times V bar transpose V is 0, right? And remember, these are just scalars. I mean, V bar is a vector, so V bar transpose is a row vector. When you dot it, when you multiply this row vector by V, you get a 1-by-1 matrix. And we're just thinking, so these are 1-by-1 matrices. You can just think of those as numbers. Okay, these are going to be complex numbers. So we have this, we have a product of this and this equaling 0. Right, 0 is the number 0, not the 0 vector. So you have this number, lambda bar minus lambda, times this other number, V bar transpose V, right, these are complex numbers, equaling 0. So if you can show that V bar transpose V is not 0, okay, then we can conclude that lambda bar minus lambda equals 0, in which case lambda bar equals lambda. So suffices to show that V bar transpose V is not 0. And why is that true? Well, this is just a general fact, because if V bar, let's say if V is, let's say it's just, Z1 through Zn, right? Then V bar is going to be Z1 bar to Zn bar. So V bar transpose is just, well, V bar transpose V is just going to be this row vector times this vector. And so this is just going to be Z1 bar Z1 plus dot 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 plus Zn bar Zn. And this is just going to be the magnitude of Z1 squared. Right? There's this fact about complex numbers that if you take a complex number and multiply by its conjugate, it's the magnitude squared. So it's going to be this plus dot 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 plus Zn magnitude squared. And of course this is going to be positive because V is a non-zero vector. And so at least one of these terms is going to be non-zero, and so the magnitude, the magnitude squared will be positive, so this will be positive, right? And so now we're done. That's the proof. Okay, so not an obvious proof. I mean, it's not obvious that we would consider lambda bar V bar transpose V, but it turns out that this ends up working. Oh, and I just want to emphasize that these are the arrows for V, and then I just removed the arrows once I started talking about complex conjugates because it would be too cluttered in terms of the notation. Okay, so that's a proof that we have this important fact that when you have a real symmetric matrix, all of its eigenvalues are real. So in particular, we can talk about, what's the biggest eigenvalue, right? What's the smallest eigenvalue? You can't talk about the biggest and smallest eigenvalues when you're talking about complex numbers, because you can't have one complex number being more than another complex number if they're not real numbers. Okay, so more on symmetric matrices later.